Got a new topic for the AQA exam question walkthroughs. So this is the first one for the equilibrium topic. Hope you like the video, hope you find it helpful, and if you haven't already subscribed, I'd love you to do so. But as always, the link to the questions in the description of the video if you want to try it first. Okay, so make a start. So for the first part of the question, we've got these two graphs here that we've got to use to deduce the optimum conditions for the industrial conversion of methane and steam into the gaseous products. So we're going to talk about two things in the graphs. We're going to talk about the trend in the graphs, and we're also going to talk about the rate, and then we're going to use that information to come up with our optimum choice for temperature and pressure. So starting with trend, so you can see in the temperature graph, as the temperature increases, the percentage conversion increases, but it does start to plateau at about 820, so we'd need to mention that. And in the pressure graph, as the pressure increases, the percentage conversion decreases. So just based on those two trends, we could argue that we need a high-ish temperature and a lowish pressure. But now if we think about rate, we know that obviously a high temperature leads to a high rate. So a highish temperature is what we need, but remember we're not going to go past 820. However, a low pressure leads to a low rate of reaction. So we don't want the pressure to be too low. So in terms of temperature, I'm going to go for around about 800 degrees C. And in terms of pressure, I'm going to go for around about 2000 kilopascals. Moving on to part two, so I've already populated part of the ICE table. So there's the equilibrium there. Initial moles of carbon monoxide, 20.1. Initial moles of hydrogen, 24.2. Obviously you wouldn't have any methanol to start with, but we're told that at equilibrium we've got 2.16 moles of methanol. So looking at the mole ratios, if we've produced 2.16 moles of methanol, we're going to use up 2.16 moles of carbon monoxide because of the 1:1 ratio, but we'll use up twice as many moles of hydrogen. So that means at equilibrium, we're going to have 17.94 moles of carbon monoxide and 19.88 moles of hydrogen. So moving on to part three, it's the same reaction, but we've got different moles at equilibrium. So we don't have to do the ICE stuff, literally go straight to the equilibrium moles, work out the total moles, and then we can work out our 3 mole fractions. So there's my 3 mole fractions. You just do the moles at equilibrium divided by the total moles, which was 7.63. So from this, we can now multiply these by the total pressure to get our partial pressures. So there's the 3 partial pressures there. All we need now is the Kp expression, and we're going to put these numbers in. So there's the Kp expression, there's the numbers. Just don't forget to square the hydrogen partial pressure. So Kp is coming out at 9.41 times 10 to the minus 7. The range allowed in that question was 9.39 to 9.50 times 10 to the minus 7. So as long as you're within those numbers, you'll be fine. So we'll just quickly look at the units. So you can see you've got kPa on the top and kPa at the power 3 on the bottom. So we can cancel out 1 on the top with 1 on the bottom. So you're left with 1 over kPa squared, which is going to be kPa to the minus 2.